All right, good afternoon, everybody. Welcome. Thanks for coming. All right, so I'm super excited to welcome Professor Greg Nemet from the University of Wisconsin, the Follette School of Public Policy this afternoon. He recently wrote a book called How Solar Energy is Cheap. You might wonder to yourself, why did the NERS chair ask somebody to come to the nuclear engineering community to talk about solar? It's because, for those of you who read the newspaper, one of the things that nuclear is struggling with at the moment is that it's too expensive. And I think there's a lot of wisdom in all of this as to things that our community should be thinking about that the solar community figured out. Right? I go back 30 years, solar was too expensive, it was niche, it was never going to happen, and suddenly we're building a lot more than we ever imagined. Right? And sort of that's why I invited Greg to come to this. I should also say on a personal note, we actually wrote this one paper together once. And it's like one of the favorite things I ever wrote.
Yeah.
Right? And it was sort of flipped, right? I was saying at one point nuclear was the it technology and it was taking off like crazy, and we messed some stuff up. And it was kind of like, dear renewables people, you should see what we did wrong and please don't. Right? I don't know anyone ever wrote it, right? But it was fun to write.
Yeah, it was fun to write, yeah.
All right. So anyway, with that, Greg has left 2 books, right? So if you really like this, then it's up to you to convince me why I should give you 1 of 2 books. That's like the big challenge after. Right, so with that,
Great, thanks a lot, Todd. It's great to be here. Nice to see such a full room. I'm really impressed that you guys show up on a Friday afternoon to talk about a technology that's outside your department, but I'm sure pizza doesn't have anything to do with that either. So, but just to start out, my perspective, and this goes through my research and teaching and why I chose to write a book, my perspective is that I think we can make better choices about the technologies that we're going to need to develop to address energy problems and climate problems if we better understand how technologies have developed in the past, and especially if we can understand how successful technologies have developed. And solar has been a successful technology for the trajectory that Todd just outlined. So that's kind of where I'm coming from. And really, when we're talking about where solar is and having access to cheap, clean solar electricity, that's helpful. But I really think maybe even more helpful is the lessons that we can learn and apply to other technologies. And maybe there's even nuclear technologies that can pick up something from some of the things that have worked with solar. And so that's where I'm going with this solar story. It's what external validity is there in terms of generalizing this case and thinking about where it might apply elsewhere. So the 3 points that I'll make in terms of answering this question of how did solar energy get cheap is, one, that no one country did it. No one country persisted in taking the technology from an idea to a commercial product to widespread deployment. Every country that was ever leading in whatever aspect of the technology was most important at that time gave up their lead after a few years. Every company that was the most dominant producer of solar panels in the world never stayed like that for more than 2 or 3 years. It was really a sequence of countries and companies within them contributing something unique and distinct. And it was much more, instead of a competition, it was much more of a relay race, of a sequence that really goes in the order of US, Japan, Germany, Australia, and China. And I'll focus on 3 of those cases when I talk about the solar case. So that's the first part, no one country did it. The second part is how important international flows of, I'll just call it knowledge, international flows of knowledge were in supporting that chain of development and the value chain that emerged from that. It was flows of information moving around the world, so you can think of scientific publications and scientific conferences. It was maybe non-written down know-how that was in people's heads that got moved around the world when people relocated from one country to another and took expertise with them and applied it in some new domain. It was machines moving around, especially production equipment was crucial in getting the cost of solar to come down, and that moved across countries easily. And then ultimately, it was finance that was moving across countries and the final products being produced and that could be shipped anywhere around the world quite easily. So those international flows of knowledge embedded in people, in machines, and in final products were crucial to catalyzing this global innovation process. So that was the second main point. And then the third main point, and this is really about external validity, applying it to other technologies, is that even though solar was a success, it happened way too slowly. So that if we're thinking about taking the solar model and applying it to something new that we think we might need for energy and climate problems or think might be useful for those, we need to speed that process that I'll outline in a few minutes up by a lot. And to one comparison I'll put out, they're probably like on the order of a factor of 4. So it took 60 years to go from the first commercial purchase of a solar panel, which was by the US Navy, to the cheap solar where we're talking about power purchase agreements under $20 per megawatt hour. 60 years is too long to apply to other technologies. So a key contribution that I guess I'm continuing to work on is how do we accelerate this process? How do we speed up this development process? So that's where I'll get to, and let me just kind of talk about the story a little bit. But let me first start with a little context. First, I want to acknowledge my research team that I worked with, a really interdisciplinary team that brought a lot of expertise and a lot of international experience that was really helpful, but also made it really fun to work on this project. So those were great people to work with throughout the research phase of this project. The second one, and I'll just make this point, I make this point in my classes on energy policy. It's kind of a central theme of the whole class. I start out by trying to tell people that transitioning our energy system to deal with energy problems and climate problems is hard for 3 reasons. So one is that we disagree on what we want from our energy system. I think we'd all want an energy system that's cheap, clean, and reliable, but we disagree and have very contentious debates about which one we should prioritize. Should we prioritize the affordability, the environmental impact, or something that has to do with security and reliability? And we've had really hard discussions and choices, and people have really different perspectives on what's most important there. So my perspective is innovation can help relieve some of those trade-offs and have solutions that achieve all of those in a less contentious format. But for now, we're often dealing with these trade-offs. Second, if you look historically, and if you look at transitions from one primary energy carrier to another, this is 150 years, 160 years there. It took on the order of half a century to go from a bio-based economy, which is what we had 150 years ago, to one on which the Industrial Revolution and a lot of economic growth came from, which is one based on taking advantage of the chemical bonds in coal, and then one where transportation became huge and oil became the dominant energy carrier. But even though we knew in the early 1900s that oil is transformative for mobility, it didn't become a dominant energy carrier until the mid part of the 20th century. And so this slowness of transition, probably in large part because how long stuff lasts in the energy sector, is really different than other areas, but is something that kind of has an inertial force on how things look. And so we might need things to change faster than they have in the past. And then third, if we think about the climate problem, when you put CO2 in the atmosphere, and this is a really crucial point that I think a lot of people miss, and what makes it so different from some of the problems that we've dealt very successfully with in the past, environmental problems, like taking sulfur and getting rid of sulfur and getting rid of acid rain and dying forests and lakes. When you put sulfur in the atmosphere, it rains out in a matter of days to weeks. Same with particulates that lead to health problems. When you put CO2 in the atmosphere, it stays up there, half of it for something like 100 years. So that leads to more kind of inertia and more slowness of the system to react. So one thing that, in making these points, I realized I was getting really good at making these points, and as a consequence, I felt like people are coming away from my classes and my talks quite discouraged about us actually making the type of change that could deal with some of the problems that seem real because of the contentiousness of the debates, the slowness of the system to react, and then the inherent inertia in the climate system. So I started starting to kind of write down and have ultimately closing some of my courses with reasons why I still continue to work on this problem, even though I think it is really hard for these reasons. So I started putting together a list of reasons to be optimistic about dealing with some of our energy and climate problems. And it would be fun to do a whole talk on all these reasons for optimism, but I have to say, over time, this list has gotten longer to me. It's also, each of the points on it has gotten stronger and I think more convincing to myself and to others. And then I also realized that for other people, there's completely different points that they would see as their reasons to continue working and be optimistic about it. But I think the number one that I still find most compelling is that even with climate change, 30 years of really going from strong awareness of the problem and politicians dithering about what we should do about it. In the background, we've got technology improving. And as I'll say in a few minutes, it's on a variety of technologies, of them getting more efficient, of using less materials, of reducing the manufacturing costs, of performing better, of starting to get consumers more comfortable with them. And so I think that really underpins a lot of these other elements of reasons to expect we can actually have some of the change that we need, and a lot of it has to do with the technology underneath it. And so that's what really informs a lot of my work, or motivates it, and that's what this book is really about, is on this point number one, and why I think there is real reason for optimism. So the second point I'll just put up here is just to make the case with a little bit of mostly US data, but a little bit of others, is to look at how far things have come. And it's not so much about where we are now with solar that I'm interested in. It's more the trajectory. It's the slope of this line. So this is 2016 dollars per megawatt hour. I guess I don't need to explain what a megawatt hour is in this room, but in other rooms that I've been in, I do say that a megawatt hour is the average residential electricity use for a US single-family home. And so you can think about it as your monthly electricity bill in terms of these units. So it's like dollars per month of electricity. So grid electricity is something like $120 a month, and that's been pretty stable. If we look at the average cost of solar, that's been going down over this 20-year period here. And then these blue dots are 1 million data points of US households that have installed solar. You can see a lot of dispersion there, so some really expensive systems, others that are cheaper than grid electricity. And then we've also got larger scale. These are utility scale plants in the US, and then we've got a few at the bottom there, those open circles right here, that are utility scale plants in other countries in very sunny locations. And this is took out all subsidies out of this one. And so if we just zoom in on this point here, you can see that some of these plants are down around $20 per megawatt hour. Those red dots on your right for 2030, this is an experiment we did called expert elicitation that we did around 2008, 2010, where we found solar experts, interviewed them for half an hour to an hour each, tried to elicit probability distributions in their head about what the cost of solar would be in 2030. And so we have their highest cost outcome, worst case, that we call that 90th percentile, most likely case, and then in a low cost case, like at their 10th percentile. And now, taking those 2010 interviews, or expert elicitations, that's the red dots there, and comparing them to power purchase agreements in multiple countries, we've now got power purchase agreements in 2018 that are below the most optimistic elicitation from the most optimistic expert for 2030. So people got surprised. Even those that you would think would have motivational bias to talk about how cheap solar is going to get, they didn't expect it would be as cheap as it is. And so I think that's interesting that it's beyond expectations. What I really want to get at, though, is kind of the slope of this trajectory of the line, because solar's had this rate of improvement that's been more than any other energy technology, and so I really want to do is try to understand that. The other thing that makes it interesting is it's not the only one. It's not completely a case by itself. So if you look at solar, PV, if you look at wind and batteries, they've been on similar long-term cost declines. The wind one goes a little bit longer because we had some expert elicitations about the future. Batteries, the slope of that line looks quite a bit like solar, and potentially with a lot more room to run in terms of power and energy per cost of the battery. So there's more going on here than just solar. So I guess the other question I had to answer in this project is, why write a book? So I've been working on solar data since the beginning of grad school for me, and I've been really collecting as much data as I could. We've got some pretty nice data sets, like this 1 million homes in the US that we have prices for every single system that went in, and you can identify some of the factors and identify some of the cost reductions. And I've done a lot of that work with econometric models and bottom-up engineering cost models. But along the way, I kind of had this feeling that there was things missing, things that were hard to measure, that were hard to operationalize and turn into variables that you could put into a model. And that was what this book project was really about, was to identify omitted variables, things that seemed like they might be important, that hadn't shown up in some of the quantitative data before. So that's why I wanted to try to write this book. So it was 3 questions. How did solar become cheap? Why did it happen as it did in terms of how long it took? And then how can we apply that to other technologies? So let me just, show you what I found here. The first thing I talk about is I talked about some of the solar costs. If you go all the way back to the late 1950s, that's that first commercial solar sale, it's 4 orders of magnitude of cost reduction. So a factor of 10,000 from the first solar cell that was originally produced by Bell Labs, and then an entrepreneur called Les Hoffman in the late 50s started making small ones, and then got a contract to the US Navy to power one of the first satellites after Sputnik called Vanguard 1, and so that was the first application of solar. It was a launch in 1958, and that tiny solar cell to just transmit information back to Earth cost about $300,000 per watt in today's dollars. So that's an expensive, remember, or $300,000 per megawatt hour. So that's your electricity bill if you did your whole household on those little Vanguard 1 solar satellites. So that's where it starts. There's a front page of the New York Times the day after Bell Labs made their big breakthrough there that said, here's the technology for the future. Solar could power the Earth's energy system. And that was big expectations, and really nothing happened for the next 20 years. And really the big push in the US was on nuclear power in the 1950s and the 1960s, and there was huge deployment that happened after that push. Then we have 1973 October, Arab oil embargo. The Arab oil states refused to sell oil to the US, to Japan, to the UK, the Netherlands, and Canada. And as a result, those countries, but especially US and even more so Japan, decided to get really serious about finding ways to produce energy domestically. And that launched Project Independence. That was President Nixon's plan to have the US import no foreign oil by the end of the decade, by 1980. And that wasn't achieved, but there were a lot of improvements that happened, but there's a lot of funding that went into R&D, and a lot of it went into nuclear, a lot of it went into finding ways to turn coal into synthetic fuels, and then a little bit went into solar. But for solar, that little bit was gigantic. It was like $1 billion of R&D that went in the late 70s into the early 1980s. And you had a couple things that came out of that. So technical improvements, so efficiency went way up. It entrained a lot of people. So people moved from the space program, the Apollo program that had just finished up, and were starting to work and taking some of their skills to photovoltaics. And people came from other industries as well. And one of the most important people there was a guy named Paul Maycock. He came from Texas Instruments, where in the 60s he'd been working on building calculators. And they had developed this idea, and were measuring it, that as they built more and more calculators, the cost per unit were coming down. And there was kind of an idea behind this of the learning curve, that as you build more units, you find ways to spread fixed costs over more and more units, or you make incremental improvements, or you get experience that leads to developing new ways of doing the manufacturing. And so Paul Maycock said, why couldn't we do this for solar? And so he came up with this graph here. And this is me kind of replicating his graph, all the data except for one point, and all the axes are from Paul Maycock from 1975. And so what he did is he just took the costs from 1958 to 1974 and applied what he called a learning rate. So a learning rate is what happens to costs when you double cumulative capacity produced. So he said with calculators and the other things Texas Instruments had built, it's between a 10 and 30% cost reduction for every doubling, and 20% is a good kind of mid-range number to use. And so he just forecasted that into the future using those early 15 years of PV production data. He had one interesting way that he thought about it too, is this calculation here. And so here he was saying, this is the extra investment it would take to get solar down to what he thought would be grid parity, so where we wouldn't need to subsidize it anymore. And so in a way, you can maybe think of it as a triangle that starts at whatever number you think is grid parity, and goes up to here, and you would need to subsidize that amount above the regular electricity price in order to move capacity to the right on this axis, and that costs would follow. And then I just plotted 2018 on it, and you can see Maycock's projection is pretty prescient. He didn't take that much data, but there's something about this learning curve that did seem to work really well for calculators, and it's worked really well for solar. I mean, well, in terms of being pretty accurate prediction of what happened. And then there's also a real policy implication that comes out of this idea is that, maybe what you do is you get companies to pay for this, or maybe you get the public sector government, that's subsidies, to do this, so that eventually you don't need to subsidize it anymore. And I think that's one of the most important ways to think of subsidies for solar. The subsidies aren't really trying to get us the benefits of clean energy. The subsidies are trying to get us to the right on this learning curve to get the cost down so we don't need to subsidize it anymore. And if the costs keep going down, then you start having social benefits, say if this is grid electricity, that start paying back the subsidies. And remember, this is a log scale, so a small triangle here is worth a lot of public benefit, and this is the subsidy that you need. And so if the one country that really took this idea and ran with it was Germany in the early 2000s, and they did a subsidy program that added up to about $200 billion, which is a lot. And it's not, a giant country, but it's pretty in line with Maycock's estimate. So if you take $1975 and account for inflation, that $10 to $20 billion looks like something like $70 billion in today's dollars. So maybe the Germans paid too much, and there's a lot of people think that we could have gotten the same outcomes from the Germany subsidy program with maybe half that much subsidy. There's something about this projection that I really like because it got a lot of things right. I'll come back to the German case in just a minute. So going back to this overall picture, we've got Project Independence, Project Sunshine. The other thing that was an important development, and this is one of the things I think was really lost in the solar story, was there was a policy in 1978, US federal government, called the Public Utilities Regulatory Policy Act. And it was just a way to say that small-scale producers of electricity should be allowed to put power onto the grid and should be compensated for it by utilities. And that also that utilities needed to compensate those producers at the utilities' avoided costs. So what it would have cost them to produce that power separately. And so it's kind of an arcane federal law from the 1970s that gets mostly forgotten about, but it starts to get implemented in the 1980s in California, and really for the wind power sector. So we start seeing it implemented in California, and it's really hard for these small-scale producers to negotiate with the large utilities. And so what the Public Utilities Commission in California did is come up with standardized contracts. So it said, here's the legal language, it's all right here. We'll come up with a schedule of rates for the next 10 years. And if you qualify for being able to commit to provide reliable power to the grid, you can get this reimbursement rate. It was like 12 cents per kilowatt hour. So a pretty generous rate, and you're guaranteed that rate for 10 years. And that became known as the Interim Standard Offer Contract number 4. That's that data point there from 1985. And it was dramatic, not for solar. Solar was still too expensive, but it was for wind. So about $2 billion of Wall Street investment went into California wind farms in kind of 3 mountain passes in California in the early into mid-1980s because they were getting this almost a guaranteed return for 10 years on the electricity they produced. And people around the world saw that you could catalyze investment by giving certainty to the producers, and the Germans especially saw that. So that was a policy innovation that the Germans later pick up. I'll talk about that in a minute. The next one we're talking about is Japan, and Japan keeps the solar industry alive in the 1980s and 1990s. The US really kind of divests from solar in the early 1980s. It cuts R&D funding over 2 or 3 years, from 1981 to 1984, by almost 80%. So it gets down to about 20% of the highest level, which is 1980 to 1981. And so the research frontier goes elsewhere. It especially goes to Japan. A lot of the people move around and start attracting interest in Japan. Electronics companies in Japan, thinking of Panasonic and Sharp, start getting interested in solar. They had some experience with it from this R&D program and started doing it in funny ways. They started putting tiny solar panels into watches and calculators to distinguish their products. A tiny market, makes no difference to global energy supply, but it got large companies familiar with the technology, and they started seeing that there was a way to differentiate their product and start to use it a little bit. And then all of a sudden there's industrial support for what Paul Maycock would have liked, which is a subsidy program. And that's the rooftop program in Japan from 1995 to 2004. So about 200,000 homes install solar on Japanese roofs. It's the first time that we give a subsidy to consumers, so you get about half off, a half value rebate for your solar system, and to see people actually embrace it. So 200,000 customers decided to take that on and get 50% off discount on their solar system. So that was a policy innovation. The other innovation that Japan did, and this also fits with this Maycock learning curve idea, is that they weren't going to continue that subsidy forever. They said it's 50% in year 1, it's going to go down to 0% in year 10, and it's going to go down on a predictable schedule each year, and so that the subsidy will go away over time, with the idea that we wouldn't need to subsidize over time, because as the technology gets better and gets to scale, the cost would go down. And so that was another policy innovation. And so the Germans take that up next. So I'll do my own little picture for the Germans here. So, and I've got the sequence on the top of the slide here, but just to really simplify it, if I just take a break to do the overall picture here, if you think about 3 countries making contributions, I think that explains a lot. The US created the technology, the Germans created a market, and the Chinese made it cheap. And it was in that sequence, and it made sense to be in that sequence, and each of those places added a distinct set of efforts and capabilities that really led us to the solar today. So I just want to highlight the next 2 parts of that story, the German part and the Chinese part. So the German part, first of all, and this is really coming from political science and my policy work, a policy window opened up. So in 1998, the Green Party became part of the ruling coalition for Germany. And the Green Party had been advocating for solar for 2 decades, had a few experiments in German cities, and all of a sudden they had their opportunity. And so it was Hans-Josef Fell on the bottom there, who is the head of the Green Party, and a social democratic leader named Hermann Scheer on the top there. And together, Hans-Josef on the bottom wrote the policy, and Hermann Scheer sold the policy. And when it was only a few years that they had this coalition with the Green Party in power, they passed this subsidy program. And the writing was an important part of it. It's a process of policy diffusion. So they took this idea from the US, from the California implementation of PURPA, these guaranteed contracts. They saw what happened there. So they said, okay, we'll give above market prices. And the Germans gave way above market prices, like 52 cents per kilowatt hour. And California was giving 10-year contracts. The Germans gave that for 20 years. So it was an amazing deal for anyone to jump in to that market. And as a consequence, people were borrowing money at like 2% because it was such a guaranteed return for 20 years there. So they took the idea from the US of these guaranteed contracts, and they took the idea from Japan of subsidies direct to consumers and a declining rebate schedule. And that led to the passage in 2000 of what's called a feed-in tariff that was really strengthened in 2004 and then really created a demand. So that's what we sometimes call demand pull. So these are installations in Germany, and you can see there's a little bit of rise in the early 2000s. But with that policy change in 2004, the German market increased by a factor of 4, so 300% in 1 year, and rose after that and stayed high for like 5 or 6 years. And all of a sudden, solar was taken seriously as a business opportunity. And there was a lot of kind of stability and credibility because of the way the policy was designed with these 20-year contracts. And so what that really led to, what later became, the Germans called their gift to the world. And this is a little bit ironic in that, the Germans spent $200 billion on these subsidies, eventually almost all the manufacturing happens in China, and people are kind of like, well, why did you do this, Germany? And so there's a few different ways to answer that question. One is that the equipment suppliers in Germany have done very well supplying to the Chinese, and the consumers of electricity have done very well buying cheap solar panels from China. But also, it's our gift to the world. And so this was this idea of kind of Germany being a eco-innovator and leader. But when I say the gift to the world, I think of it a little bit differently. They created this market that was so large and had so much credibility behind it that it led to investment. And it wasn't just lots of people saying this is a no-brainer to spend 10,000 euros and put a solar panel on our house and get a large return over 20 years. There was that investment, but the really important investment was that manufacturers, and even further up the supply chain, equipment suppliers to manufacturers, people that were producing specialized equipment like this wire saw here that would saw silicon ingots really thinly so you get many, many solar wafers out of the same amount of silicon. They could now start producing equipment specifically for the solar market because it was big enough to devote R&D to devote engineering resources to, instead of what they had been doing, was just take cast-off secondhand equipment from the semiconductor and computer industry and repurpose that for solar. And there were a lot of efficiencies and cost-reducing opportunities that came out about using equipment just for solar because you didn't have the need for purity and the concerns that are really important in the semiconductor industry when you're just trying to convert sunlight into electricity. So that led to all this investment and these machines that came up. So that's the German story. And so I really think Germany's gift to the world is this creation of a market that stimulated investment in China and then in the US, in Switzerland, and other places that were making these machines that the Chinese then bought. So that brings me to the Chinese part of the story. Oh, and this is just some of the, if you say, why did it get cheap? So plants got bigger, the efficiency doubled over this period here, silicon prices went way down, wafers got wider and they got thinner, so thinner because of those wire saws, and then yields increased as well. So all of these changes were happening at this time of increasing demand. And then the China story. And so if the US made the technology, Germans made a market, the Chinese made it cheap. And this is how it happened. And it really is two phases. It's one, the early 2000s, and then the second phase is after 2009. And in that early period, it's entrepreneurial, it's really the Wild West, it's a few scrappy innovators pulling some things together and scaling up and being very successful with that. After 2009, the central government gets much more heavily involved. It sees the industry as a winner and it champions it and funds it a lot. But it didn't really fund it much at all before 2009. So this early period, this scrappy startup, I think one of the most kind of revealing anecdotes or kind of stories that makes the case for this international flows of knowledge was this group in Australia that started hiring Chinese students. And it was in the early 1980s, Deng Xiaoping had this program for 1,000 Chinese students to go overseas and come back to China to see what they would learn and to see how they could make use of what was going on in the rest of the world. And one of those 1,000 went to the University of New South Wales in Australia, and he had some experience with microelectronics, and he was hired by the guy on the left there named Martin Green, and he had good experience with that student. He said he was quite well trained and he could contribute to the lab, and he hired 3 more students over the next 10 years. And then in the early 1990s, he hired another student, and that's the guy on the right in the picture there. And in 1994, he brought that student to China to explore the possibilities of setting up production there. And that student then was a translator for the trip. That was the only role he had. And they came away from that trip just saying there's no possible way you could manufacture in China. There's no infrastructure, there's no supply chain, there's no interest by any of the cities in setting up manufacturing there. There's certainly no investment to do it. And so they left after that trip in 1994, and they went to India to set up manufacturing of solar in India. And that didn't work either. So then they went back to Australia and set up a company called Pacific Solar in Australia. About 5 years later, that translator started talking to his Chinese friends back home who were saying, things have started to change here. You should take another look. And so in 2000, he went back and started talking to cities about setting up manufacturing. And still, it was pretty hard to get something to happen. But one thing that had changed is that cities now could retain some of the tax revenues from manufacturers and other companies that were located in their cities. And so all of a sudden the cities were starting to have incentives to attract investment and to set up manufacturing. And so they were able to get $5 million to set up a tiny manufacturing line. And so this guy, this Zheng Guangxi, who's in the picture there, traveled around the world, bought secondhand equipment, brought it back to China and set up a manufacturing line. And this was just around the time that the German market was starting to take off. And so he said, you know, we can sell to the Germans. And he tried to sell the panels to the Germans. And the Germans are pretty skeptical. They're very proud of their own engineering process, quite skeptical of the Chinese quality of those panels. But Xi had credibility because he'd been working in this University of New South Wales, and they were achieving world record efficiencies on the cells. And so the Germans really respected that and saw that he had the technical credentials to make something that would be reliable and technically sophisticated. And so he started selling to the German market and started this process of iteratively scaling up. And by 2005, that company that he started, I'm forgetting the name of it right now. Oh man, what is that name of that? All right, it'll come back to me. Oh my God, I've spent so much time researching this company. Man. Anyway. Okay, so he starts this company. It goes public on New York Stock Exchange, raises $300 million. And so all of a sudden, solar is a legitimate company. So this, just to put this in perspective, this is again, this international flows of knowledge and money in this case. So it's US pension funds that are taking their retirement investments, putting into the stock market. That stock market is going into these Chinese solar companies, including this first one here. The Chinese are taking that money, so it's $400 million, taking it to China and using that to buy equipment from the US, from Switzerland, and from Germany, taking that equipment, installing it in China, and then producing panels that they sell to Germany, later to Italy, to Spain, to California, and then ultimately China itself becomes the biggest solar market. And so a few things that happen with that. So we've got used equipment coming from the US, we've got pension funds, and then we're selling to Germany. So these international combinations of knowledge are so crucial to this whole story. And this guy, Zheng Guangxi, who was a translator on that 1994 trip, became the richest person in China from 2005 to 2007. And then they ended up buying an Italian company that had some fraudulent loans, and the whole thing went under. And so by the time I talked to him about a year and a half ago, he didn't want to meet with me. He needed to be a little bit quieter about his location. But one thing that, even though his story didn't end very well, the solar industry really legitimized itself by this pathway, especially being able to sell to a market like Germany and be able to attract investment from the US. Those two things really legitimized it, so that by the time we have the global financial crisis in 2009 and 2010, the central government's willing to put 20, maybe $30 billion of low-cost loans into Chinese solar companies to keep them afloat when these Western subsidy programs were ending because of the global financial crisis in 2009 and 2010. And then eventually the Chinese themselves start subsidizing solar and have their own feed-in tariff. And then by 2013, China is the largest market in the world for solar. And then just two aspects of the Chinese case that are important to appreciate is that in the 2000 to 2008 period, Chinese labor cost advantage was very helpful. It was so much cheaper than trying to do production in Germany and some other places like the US at the time. And so that was a big advantage. But by 2008-9, because of that investment in equipment and machines that was really developing in response to the German market, it was almost completely automated. And so the labor cost advantage was not really serious. It was really about how do we get automation to go well and to integrate our manufacturing lines and have supply chains that are very tight with lots of information flowing very quickly. So that was a big part of the Chinese story, was lots and lots of automation. And the other part is that top graph there, lots and lots of competition. So when the US was dominating solar in the 1990s, we had companies with 30% of the world market. When Japan was in the early 2000s, that's Sharp with 25 to 30% of the world market. But even with the Chinese companies becoming giant and scaling up, and even in with this original company whose name I finally remember called Suntech, none of them ever got above 10%. So it was extremely competitive. And so margins in the industry go way down, and that was another big reason why costs came down as well. So this is kind of, China's gift to the world then is this cheap electricity and the potential to have 30 or 40% or 50% of electricity by mid-century from solar. Okay, so, and then this is just a picture, because it's actually pretty hard to get into these places, of solar manufacturing in China. And this is to make my point about automation. Like, how many people do you see in this picture? It's a few reflections of people gawking at the machines doing their things here. It's really about pulling these machines together, optimizing them, and they used a lot of know-how from Applied Materials in the US and some German companies to come and string those together and set up their production lines. But now they're doing that on their own, and they're making most of these machines on their own as well. So just to now, with the last few minutes here, to make an effort towards external validity. So how can we kind of come up from all these stories and anecdotes and history and think about it in kind of a stylized, reduced form way that we might apply to others? And the first thing I think is helpful to think about is these kind of three stages, is creating a technology, building a market, and then getting the costs out. And in terms of creating a technology, Einstein played a key role here. So his Nobel Prize was for a paper on the photoelectric effect. And the scientists at Bell Labs that came up with the first efficient solar cell used his idea of activation energy as they were working on making these PN junctions on the original solar cells. We had R&D that was crucial throughout this time, but changing the focus. So looking at configurations and design, but then looking at different materials and R&D on manufacturing itself. That was really important throughout the time. And then knowledge spillover. So it wasn't all confined to individuals, it wasn't confined to companies, and it certainly wasn't confined to countries either. It moved around, and that sped things up. So there, on the creating a technology side, those have been important components. In terms of creating demand or creating a market, creating reasons for investment, one is that, and that's a picture of Sputnik there, these niche markets, solar had the benefit of niche markets all the way along, from 1958 and the first satellite cell, then it was oil rigs, then it was people that wanted to be off-grid, then it was the calculators and the toys, and all along the way, there were small but growing, high willingness to pay but shrinking over time, niche markets. And you didn't need policy all the way along to make the technology continue. If you could find places like up in orbit where energy was really expensive and that solar had some unique capabilities that it could be applied to. A second part of the building a market story is the modular scale. So that's something that really makes these niche markets work, is you don't have to only have gigantic solar. You can have tiny solar. So think of the cell in a calculator, and then think of the largest solar power plant in the world. It's probably the one being built in Egypt right now, and it's about a factor of 1 billion from that calculator to this plant being built in Egypt right now. And almost every scale in between has been used to satisfy some need in some market. And so there's lots of different ways that you could find niches when you had that ability to have lots of different scales. And then policy support. Certainly policy has been crucial. But when I say robust, I guess it's got two meanings. Robust in that the German policy was very generous, and so it's strong robust. But robust also has this meaning of, if you take away one factor, one thing changes, you still have that incentive. And that was the case because we had lots of different countries providing policies for solar. So when Spain went into the financial crisis and cut off all its subsidies immediately, the industry didn't fall apart because you had California building up its California solar initiative, and then China created its own. And so there was never one dominant market, except for the German market for a few years, that was completely dependent on a subsidy and thus completely dependent on a political coalition holding or an election going a certain way. It really created expectations that there would be a demand because it was coming from multiple policies. And then in terms of making it cheap, there's the learning by doing aspect, and that's been certainly helpful. One of the things I got from interviewing people and talking about them setting up their companies was that they didn't go big immediately. They scaled up over time. They built one line, got it to work a little bit, built the second line bigger, maybe with a different technology, maybe with some small incremental improvements. And so this ability to not get locked into one choice, but be able to gradually make improvements along the way has been crucial for solar in general, but for the manufacturing part especially. And then the delayed system integration. So now, we think about the challenges associated with having an intermittent resource on the grid because it's not sunny all the time and there's clouds and thunderstorms and things like that. And those are serious challenges that we have to address. But solar developed for 50 or 60 years without having to encounter those problems. And now it does, but there's a lot of momentum behind it. A lot of things have been worked out by the time it has to do with system integration. And compare that to a large scale, maybe a nuclear power plant or a carbon capture large scale plant. We're building some of the first ones of those. They have to get system integration right away on a multi-billion-dollar investment. And so that is an advantage that, that solar had as well. Okay, so is it okay to go for a few more minutes? Okay. I just want to put a couple of ideas up there for how we could use PV as a model. And the first thing I'd just say briefly is it's not a model for everything. And one thing I've started to work with is sort of thinking about solar PV as kind of one distinct area of climate-relevant technologies that's got the characteristic of having a strong technology component. It has this iterative. So when I say iterative, there's been about 2 billion solar panels have been produced in the history of the industry. So lots of chances to improve, change things, learn. And then disruptive, this idea that by compromising on certain attributes, in the case of solar efficiency, you could have gains in other areas, so in terms of cost of production. So the Chinese were very savvy in producing cells that are about 2 percentage points less inefficient. So like 15 years ago, this was going from about 16% to 14%, but you could get the cost down by about half by making those compromises. And so those were characteristics of solar that I think you could maybe apply to other technologies. Then there's other technologies we might need for climate change that are really different, like storing carbon in soils or trees. That's really low-tech and distributed. Large scale, where system integration seems to be the central challenge, so like bioenergy with carbon capture, and there we need other models. So maybe we need to learn from oil refineries and chemical plants for those. Maybe the green revolution is helpful for understanding how we can get more carbon in soils, and there's general purpose technologies that will almost be certainly helpful for dealing with climate change, and we've developed general purpose technologies successfully before. So I really work on now is this first category. How do we learn from solar? So let me put up a few points here. One is that, and this, I've kind of gone through this story, but we now have several countries where we're talking about close to 10% of our electricity from solar. It's not capacity, that's electricity. And close to 2% of world electricity is coming from solar. And so that looks pretty dramatic over this 10-year period here. But if you look at my time frame, I think this is way, way too slow if we're going to say we're starting in 1958 and getting to 10% of electricity by, say, 2020. That's way too slow. And so part of the challenge here is how do we speed this up? And so as an example, I've been looking at direct air capture, where you take CO2 that's already in the air. So this is to address this issue of CO2 staying up there a really long time, and removing it, pressurizing it, and then sticking it underground. So taking it out of the atmosphere directly. So I presented this to the direct air capture companies. They didn't like this picture, but here's what it looks like. So if you say it took something like 60 years here to go from the first commercial to low cost, and then we're talking about maybe 30, 40% solar by 2040, let's take your direct air capture plants. This is the first one that went online in 2017 in Switzerland. So this is taking ambient CO2 at 0.04% concentration and absorbing it, pressurizing it, sending it 400 meters behind that plant. In the upper right-hand corner, you can see a little picture of a greenhouse there. And so that's who's purchasing this CO2. They're using it to raise the parts per million in their greenhouse from about 400 to 600 or 700 and increasing the yields on their tomatoes. So 2017, that's a real plant, is a real customer. So if you apply the solar timeline to that, they're low cost in 2076, and their widespread adoption by the end of the century. That's not on the scale that we need to do with climate change. So these are some integrated assessment model results for how we would meet a 2-degree temperature target. And if you look at those, we need to start deploying these negative emissions, these removal technologies, by 2030 in a serious way, and scaling it up to billions of tons by 2050, maybe 5 to 10 billion tons a year. So just to put that in perspective, it's like taking out of the atmosphere about a quarter of what we put into the atmosphere now by 2050. And so they need to do something, if they're going to contribute to this, way faster than solar. And just to put that in these simple terms here, they need to speed things up by like a factor of 4. And so what some of my research is trying to do now is how could we, and this I was looking at scale up for the fastest solar companies here. So log scale here. These are Japanese, the Sharp, German is Qcells, and Suntech and Jinko are Chinese. And you can see how fast they scaled up their production. If one of these companies, Climeworks is one of them, had a goal to remove 1% of the world's CO2 emissions by 2025, they would have to scale up about twice as fast as these solar companies. So it's not out of the question, but it would take serious commitment and investment and the type of activity that we've been seeing in solar, but more to do even 1% of emissions. So, and this is, I'll just stop with this one here. Part of what I've been trying to work on is how do we get that factor 4 acceleration? So we can learn from solar, we can say what happened there, but how can we actually do it faster? And so this is just some initial ideas of things we could do to speed things up, not for solar, but for direct air capture or whatever other technology you might think important. So I'm thinking of it in the 3 rows here. So on technology push, so creating new knowledge, on knowledge flows, on disseminating knowledge, and then on demand pull, creating markets. So the R&D I talked about already, having a trained workforce, scientists and engineers is crucial here. Public procurement, I didn't talk about very much, but that was a big part of the US effort in the 1970s, was for the government to start buying solar panels. That led to companies actually having to produce for a real customer. There were technical characteristics about reliability, efficiency that they had to meet. And so that really got the companies to become from kind of small scale batch producers to something more, a little bit approaching industrial. On knowledge flows, so codifying knowledge, so taking it out of people's heads and putting it into, maybe it's science, maybe it's reports and papers, but probably more importantly, data sets that people have access to and can make improvements on and understand what's happening. Knowledge spillovers, I've talked about that. So knowledge going from one person to another, company to another, country to another, and the global mobility that I've talked about quite a bit already in terms of people, machines, know-how, finance, and then final products. And then in terms of creating markets. So the robust markets part is really important. This disruptive production, so being able to compromise on attributes that consumers don't think are important in order to address issues that they do think are really important. And that might be something like cost for solar. For electric vehicles, it might be something like convenience or safety cost as well. And then the final one I'll put up there is political economy. And that is to make the point that every country that had strong effort to create markets for solar and subsidize solar eventually got strong resistance from competitors to solar or other entities that stood to lose from widespread use of inexpensive solar. And in every country, Germany, Japan, US, and China, those efforts have been successful in kind of blocking the progress of solar. And probably the best example where this has actually been resolved was in Germany, where they passed that strong policy that was in place for 7 or 8 years in a big way, and about $200 billion of investment goes in, or public investment. But they made a big compromise. They said that large electricity users, so energy-intensive industries, don't need to pay for the subsidy. Only households need to pay for the subsidy. And there's a lot of concern about fairness and ability to pay, but that was a way to make sure that those large users didn't stop the policy. And I think if we wanted things to go quickly, we might need to make those types of politically savvy moves in order to make things go quicker, because a lot of these entities stand to lose from some of these developments and can effectively slow them down. And in a lot of cases, we don't really have time. We need to be moving faster on these things. So I'll stop there and happy to take any questions either now or after we stop. So.
So how does the decrease in cost in solar panels compare to the decreased cost of computation speed or memory? Is it faster, slower, or is that trend is the same in all?
Yeah, that's a good question. I think it's faster in computer memory, because with computer memory you can do miniaturization. You can do lots and lots of transistors in the same amount of space. With solar, there's only so much sunshine hitting a panel, and so you can never get above something like 30% efficiency anyway. So you can reduce the manufacturing cost and the material cost and the thickness, but you don't have this ability to jam more and more photosensitive material into the same amount of space. So that's one thing that has made computers go faster. But there are a lot of similarities in terms of the iterations and the scale up, and even the material is the same. So yeah.
Your slide 6 makes it seem like there's no point in talking about anything else unless I'm missing something. If solar's already 1/6 the cost of market price and is projected to just get cheaper, why isn't that already like, that's it, like it's all we build, if it's that much cheaper than the market price, and how could anything else hope to catch up to it and compete?
Makes it harder for things to compete. But, you know, there's places where, you know, this is in Chile and Abu Dhabi. And so in Ann Arbor, you have probably 1/3 of the sunlight. So that triples the cost in terms of dollars per megawatt hour. So that doesn't look as good here. So these are sunny places. That makes it better. It's even in Abu Dhabi, it's not sunny all the time. And so you do need access to low-cost storage. So that could be something that you have to add to this as well. But that cost is coming down too. And so, you know, maybe storage looks like that if you add it on. And then you've got space too. Abu Dhabi has a lot of space. Chile has a lot of space. Maybe you could in Ann Arbor. But there's a lot of other places where, especially large mega cities, where the density of energy consumption exceeds the space that you have for solar radiation, even if you could take advantage of all of it or 20% of it. So yeah, so there are reasons for why other things, you know, have niches to compete. But it does make it harder to compete, because not only are these costs low, but they continue to go down. And if they're supplemented by storage that's low and continues to go down, it's a moving target in terms of competing with it. There's one at the back. Yep.
How do you calculate the cost of the megawatt hour?
Yeah, so you take how much it costs to install the system, discount it at a discount rate over a certain number of years. So they're guaranteed for 20 years. We use 20 years. And for household systems, we use a little bit higher than a mortgage interest rate. So you can calculate the amortized or the levelized annual cost that way. And then if you take how much sunshine there is in each location, so there's numbers for Ann Arbor, and you know the efficiency of the cell, you can figure out how many megawatt hours you can produce in a year. And so you divide the levelized cost by the megawatt hours that you produce, and that's our estimate here.
So the warranty time is the time you use.
Yeah.
It could be longer.
Yeah. I mean, I don't think it makes a big difference, because that recovery factor kind of approaches the interest rate once you get after 10 or 15 years anyway. So it wouldn't make a huge difference in terms of levelized cost. Yeah, it can't. Yeah.
So there's no battery or demand aspect in this. So in the way you.
Right. Yeah. There's no battery. Right. So this is just saying it doesn't matter when you produce it. We're going to count those. So there's certainly electricity valued at different levels for different places and different times, and so that's not included. It's just cost, no value. Yeah.
So we live in a state where the power companies are not so favorable, and they say it costs them more money to make power from sun and wind, and therefore they're charging us more. So could you say something about the advantages or disadvantages of trying to purchase power in a sunny part of the country to offset our use here? And how, is that real or is that a shell game?
I mean, it can be real. You just have to make sure that if you're, paying for clean power that's being produced somewhere else, that it's not just making all the other power more brown. So, but there's ways that, you can make sure that that's happening. Yeah, but it does, raise the issue about how much renewables should be happening in a certain place and whether we should take advantage of building renewables in places that are sunnier or windier. And then do we kind of account for that financially with some kind of compensation, or do we do it physically, which means building transmission, and that can be a challenge, but there's been a lot of efforts.
What is the University of Wisconsin going to do to become carbon neutral?
We have to change a lot of our thinking. I think I've been having students coming into my office for the last 3 years asking about this and why we don't have solar on all the buildings, and I keep saying, good question, ask the chancellor, and she told me they should be asking me, so I had to come up with a different answer. And then I said, okay, well, let's look into all the state regulations, because they're saying, yeah, they say we're not allowed to make our own power, and we couldn't find anything on that. And so the last thing I heard last week is that the university has a power purchase agreement where we get power for 3 cents per kilowatt hour, so that's $30 per megawatt hour. So that's here. My house has to pay this. So if you're only having to pay this and you're not in Abu Dhabi, but you're in Ann Arbor or Madison, the numbers are up higher. And so that's a big challenge, is how do you get the university to say, okay, we don't want this sweetheart 3 cent per kilowatt hour deal anymore, but we care about sustainability so much. Having cheap solar helps, and having it get cheaper helps. But yeah, it's a real challenge. And so I think we're going to need not just solar, but lots of solutions to deal with that one. Yep.
So I just want to be clear that there are no subsidies in these?
Yeah.
Or there are subsidies?
The people are receiving subsidies, but they're not counted here. So the way the subsidies work is you pay $15,000 for your system, and that's what I count here. And then if you get your 30% investment tax credit back, you get that $4,000 off your taxes, but that doesn't show up here. This is unsubsidized. But people are purchasing these things knowing that they will get a subsidy.
In one of your earlier thoughts, you had the history of the other power
Yeah.
generation technologies. It seemed like many of them had a pattern where they had an exponential growth at first, but they hit a point where they kind of leveled off. I'm talking about like coal and biofuel.
Oh, okay, yeah.
Do you expect to?
Well, that's one thing about the learning curve idea, is that it's a log scale, and so if you plotted it on a linear scale, it would look like it drops a lot, and then it kind of flattens out like it's approaching, almost approaching an asymptote. So that is kind of what we're seeing with solar. But if you plot it on a log scale, it actually looks pretty straight. I mean, this is one version of it, and this is the other. Is that what you're?
I was talking about the worldwide adoption, the percentage.
Oh, okay, so not cost, but adoption, yeah. And sorry, I missed your question then.
Do you have that slide?
Do you have that slide? It was like.
Oh, the one, yeah. The worldwide adoption of solar?
No, of everything, where you went wood, dropped, coal, paper.
Oh, that one, yes, sorry. That one.
Right, so it looks like coal, oil, and some of the others, the price of steep weights at the wall.
Mm-hmm.
Do you see the same thing happening in solar, or what is the reason for this?
Yeah, I mean, these are market shares, so it's not a total. So, oil has been growing and growing. I guess it's been flat the last 10 or 15 years, but but in terms of share, yeah, they do get to some level and then stop. But even the most ambitious people, like people that are most optimistic about solar, see it getting into 30 or 40%, maybe 50%. It's not many people are talking about it being 100% because of some of the things we talked about. It's not sunny anywhere. Sometimes you have density. Maybe you don't have enough storage. Maybe there's even material constraints. So yeah, I mean, but these are tremendously large numbers to get up to 50%. I mean, the one that's been fastest of any of them is nuclear, to get up to something like 10% in this really short period here. And so these are gigantic transitions, even though they look like they hit a wall. Yeah.
And I would just argue with, there are price societal factors that are completely cost, right? Like some of the things with nuclear that caused it to hit was not a technology question. It was, we pissed the public off in some way.
Yeah, and that's a really big part of these other technologies that we're starting to look at too is it's something that's not been a big issue for solar, but and it hasn't seemed to be a big issue for electric vehicles, but could for some of these other ones, like this direct air capture where you're taking CO2 and storing it underground. People may not want to have lots and lots of pressurized CO2 under the ground, so we'll have to see about that one. Yeah.
Okay, so we kind of went over, which is great, between your ethics, so I appreciate it. Let's thank Greg.
Great, thanks.